Okay. So we're going to talk now about a different theory that's somewhat supportive, somewhat a little bit different than Vesper and what we're talking about with hybridization. This is called valence bond theory. And what it says is there are two different ways that bonds can overlap to form bonds between the atoms. And those two types of bonds are called sigma and pi bonds. Okay. If I have a sigma bond, it is, if I have, let's say, two s orbitals, two different atoms, it's going to form a sigma bond. If I have an s and a p, it's going to form a sigma bond. So it's characterized by head-to-head overlap. So this atom colliding with this atom, and it's this head-to-head overlap. This s colliding with the head of the p as opposed to the side of the p, or two p's hitting head-to-head. So you end up getting a cylindrical symmetry of electrons, a cylindrical symmetry of electron density, okay, around the axis. Pi bonds come from overlapping side to side. So if you imagine, if I have a, let's say, my p, right, I've got 3p orbitals, and let's say, I'm a terrible artist, and you know that, right? So this is my head-to-head overlap, but if I have more than one bond, it has to come from one of these other p's. And those p's, you know, we're bonded already here on the px axis, let's say. If I want another bond, it has to come from this side-to-side overlap. Okay? So pi bonds are characterized by side-to-side overlap, and that electron density ends up being both above and below the nucleus of the atoms that are combining. Let's take another look. Okay, so single bonds are always sigma bonds. Single bonds are always sigma bonds because the sigma overlap is greater. Greater overlap with sigma bonds than you have with pi bonds. Because the pi bonds are overlapping side to side, you get less overlap than if you have this head-to-head. Sigma's head-to-head, pi is side to side. This is more overlap. More overlap, less overlap. Okay. If you have a double bond, what you have is one of these is sigma and one of these is pi. If you have a triple bond, one of these is sigma and the other two are pi. So within a bond, doesn't matter if it's single, double, or triple, there can only be one sigma. And then if you add a multiple bond, they're going to be pi. Okay, so in a molecule like formaldehyde, CH2O, we have overlapped in the sigma, right? So we have this nice, neat overlap. But then the pi bonds also overlap, and when they do, we get this overlap side to side that makes it look like this, I don't know, dog bone, right? So the overlap is in a pi fashion when that happens. So we have a triple bond. The center one is the head-to-head, and that's sigma, and then if I add additional orbitals or additional bonds, multiple bonds, they are pi. So sigma bonds themselves are stronger. Sigma is stronger than pi, but of course a single bond is weaker than a double, because this double is a, oops, I'm having trouble writing my sigmas. My double bond is a sigma plus a pi, right? So of course this is stronger than a single. But sigma bonds themselves are stronger than pi's. Okay, so that's sigma and pi. Just a little piece there. Now we want to talk about what happens with resonance. So we talked about resonance when we're drawing Lewis structures, and we said that when we have resonance structures, no one structure itself can explain the molecule, and you need to have these brackets and show multiple structures, because the double bond can be on any one of those three atoms. But in reality, what you have is each of the four atoms has a p orbital, and the p's overlap on all three around the central nitrogen. So the pi electrons are not localized between the nitrogen and one of the oxygens, but they're delocalized all the way around. So these you can consider them to be moving, right? So I have this whole plane above the nitrogen and oxygens, and another plane below where the electrons are delocalized. When we talk about resonance, benzene is a popular topic, and we talked about this when we talked about Lewis structures. And remember, benzene has 6 carbons with hydrogens attached, and they have double bonds for between every 2 carbons. And often the shorthand shows like this. But if you were to look at the hybridization, what you have is you have, side to side, 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 and side to side. On the top, you have the same thing, side to side, side to side, side to side. So in fact, what you have is you have, basically 2 circles with the carbons in between, right? So you have these 2 spheres of delocalized electrons moving around above and below the atoms. Like this. This is what it actually ends up looking like, right? You have basically a double ring of electrons with the atoms in between. And this structure makes benzene very, very stable. Okay. So